What's up, guys? As promised, I'm just going to run through the chapter 6 notes here, talking about scatterplots, association, and correlation. So we'll just jump right into it. Scatterplots are hopefully visual displays that we have all seen before. They involve bivariate data, which is simply just kind of paired data. We have an x and y coordinate now. And they're used to show the relationship between two quantitative variables. So anytime you have a scatter plot, you need to have two quantitative variables, and they come in that kind of a list of ordered pairs. And really they're used to kind of answer the question, is there an association? Is there a relationship between two variables? And these are a great way to kind of visualize that relationship. Just like when we had histograms, we kind of had our ways to describe them, and kind of our key words were shape, center, spread. We have a very similar idea here for scatter plots. Unfortunately, they don't roll off the tongue as well, but we have direction, form, strength. So every time we are describing a scatter plot, we want to make sure we mention the direction, form, and strength. Luckily, the descriptions here for the scatter plots are going to be a little bit shorter. So a lot of these can be summed up in a word or just a couple words. So let's just talk about direction first. Direction is really just going to be kind of take the form as either positive, negative, or neither. So you're kind of thinking about what would be if it was a slope, all right, what would be the slope of the corresponding line? So really, if it's a positive relationship, as the x values increase, y also increases. And that's taking place over here. This is a positive relationship. And not every single point has to follow that direction. All right, there's some that may be bigger value of x, smaller value of y, whatever. It's about the overall trend here we're interested in. Negative would just be the opposite. As the x values increase, as those move to the right, y decreases. And that's an example of what we have over here on the right. This would be in negative direction. Neither, it could either take the form of like a cloud of points, there's no real direction, or it could not be linear. It could go like up and then back down like a quadratic or something like that. So that's really all that you could do for direction. Just kind of think about it as either positive, negative, or neither. The next is form, and this is really where you're kind of describing the actual function that you would use to kind of describe the shape. So it could be linear, it could take the form of a line like we have here. It could be a cubic, or just generally curved. No pattern at all, just a cloud of points. Just basically describe what you're seeing. It's kind of similar to shape, I guess. And the last one we want to talk about, so is direction, form, and then here's strength. This is saying how closely does it actually follow that pattern that you described when you're talking about the form. And usually you want to be talking about strong versus weak, and you kind of want to throw an extra one in here in the middle, moderate. So something that looks like it's would be very strong, something that's very closely following the pattern. So here, if I draw on a line here, this is fairly strong. Okay, there's not a ton of scatter along the line. Most of the points follow that general pattern. Over here, this is very weak. We don't really have any relationship going on at all. And we'll go into more detail on kind of how to make that judgment call in a few slides here. And the last thing, this is not always going to apply for a scatter plot, but just like with a histogram, if you have any unusual features, you want to make sure to mention those. Whether those are just kind of distinct clusters in your data like you have over here, or an outlier, definitely want to talk about those as well. But those are not always going to be happening, but if they are, we got to talk about them. All right, so just an example of a description of a scatter plot. We have driver age and sign legibility distance. So taking a look at the scatter plot, it looks like it could be approximately linear here. If I was going to kind of think of that trend line. So, and it's definitely going to be negative. However, there's a lot of scatter around the line. It's not really following that pattern very closely. So I'll call it moderate. So I would say there is a moderate negative linear association between driver age Okay, you're probably thinking you barely wrote anything. Well, we hit on all three of the things we wanted to. We hit on strength right here, moderate, direction, and form. So all three were there. We provided some nice context with naming the actual variables. That is a great description of the scatter plot. There was no unusual features to mention, so we didn't mention any. So in every scatter plot, the variables have an assigned role. All right, the ones we put on the x-axis, that's what we call the explanatory variable. The corresponding one that we put on the y-axis, we call the response variable. And when you're choosing these, you want to think about how the explanatory variable kind of explains or predicts what's going on with that response variable. So here, in our previous example, where we had driver age versus sign legibility distance. Sign legibility distance, by the way, is just how far away they can read the sign when they're driving. And the driver age is what we're using to try and explain how far away they can read the signs. All right? As they got older, they're less able to read the signs. So that is why we're choosing the driver age to be what we call that explanatory variable, and therefore putting it on the x-axis and choosing sign legibility distance as our response variable. A lot of times it could go either way, depending on what you're trying to say. If you're trying to say, if you're just looking at the relationship between GPA and SAT score, and you're trying to predict someone's SAT score from their GPA, well, that would make the GPA the explanatory, SAT the response. But you could do the same thing in reverse if you wanted to use the SAT score to predict their GPA. So a lot of times it can go both ways like that. It just depends on what you're trying to look at in the data. All right, so to create a scatter plot on your calculator, it actually works quite easily. So what you'll want to do is you will want to enter data into two lists. I would just use L1 and L2. And you're going to want to make sure that you enter it properly in order, because remember, each of this data comes in an ordered pair. So these values go together. And usually you're going to want to enter X first and Y second, just so that it's easier for you and the calculator to keep track. Here, we're looking at change in tuition costs across years. So the year is definitely going to be our explanatory variable. We're using that to make predictions about the corresponding tuition. So after we have this all entered in our calculator, you're going to want to head to our stat plot menu. That we hopefully become very comfortable with. It's where we made histograms, box plots, null probability plots, and now we're adding scatter plots. And so here's what the screen will look like right here. You're going to choose that top left option, one for type, the one that looks like a scatter plot. And then you're going to just choose your X list and your Y list, and that's just coming from where you enter the data. If you didn't enter it in L1, L2, make sure you choose the right list. In terms of the mark, I would choose, it doesn't really matter, but this first one is kind of a nice one, especially if you have a lot of points. And then once you are all done with that, just hit zoom 9, zoom stat. You're hopefully becoming very comfortable with that as well. And you're all set, and that'll bring up the scatter plot. If you have an old calculator, actually no, it should be fine here. You can use the trace function. That'll allow you just to kind of scroll through all the points. If you have an outlier, you maybe want to scroll to that point, see what's going on there. But other than that, it works pretty easily. You shouldn't need to really mess with things around after you've done a zoom stat. The calculator should set it up properly for you right from there. All right, so as I hinted to earlier, we said we wanted to kind of figure out a better way to talk about the strength of an association instead of just kind of vaguely referring to it as strong, weak, or moderate. We want to have a numerical value. This is stats. Love having more summary statistics. And so in creating this value, we want to remove the units so that we're able to kind of compare across data sets very similarly to kind of how we did a z-score. So what we're going to do in order to create this measure is we are going to take the z-score of each ordered pair, basically kind of convert every single xy coordinate into the corresponding zx, zy coordinate. And so what we mean by that is basically changing each coordinate into its observation minus its mean divided by its standard deviation, and that's for each x coordinate. And you do the same thing for each y coordinate. So minus the mean y value divided by the standard deviation of y. All right, and so this was like just an example of what it looks like after you've taken all those z-scores. Right here at 0, 0, at the origin there, that is the mean x, mean y value there, x bar comma y bar. And so values over here are positive. Sorry for that squeaking, there's a little dog in the background. But values over here have positive z-scores for both x and y over in this region. Over here, negative z-scores, both x and y, working very similar to a normal xy axis that we've seen. So once we've taken the z-score of every coordinate, this is going to be the formula for what we call the correlation coefficient. We give it the letter R, and what it is you are summing up all the products of those z-scores, so the z-score for every x value times the z-score of every y value, summing that all up and dividing it by n minus 1, with n being the number of pairs of scores. So basically the number of ordered pairs in your data set. And that's going to give you a nice clean number, R, that we'll use to describe what we call the correlation here. And obviously you're never going to have to do this formula by hand. It is important to kind of know where it's coming from. But the vast majority of the time we will get this value from our calculator, which I will show you how to do in a second. A very important thing about this correlation is in English we kind of use correlation just to vaguely kind of mean the same thing as association. Not the case in statistics. Correlation is strictly reserved to measure the strength of a linear association. Okay, so we can never use correlation to describe like a quadratic relationship or a cubic relationship. This is all about a linear association. So in order to calculate the value of R from a data set, it's got to meet these three conditions. The first is quantitative variables. Both your variables need to be quantitative. That should hopefully go without saying if you already have a scatter plot. The second is the straight enough condition. And this is going to be very similar to when we were checking kind of the histogram in order for us to use a normal model. We wanted to check if it was unimodal and symmetric. Here, we just want to check the scatter plot and make sure it's roughly linear. So that's why we say straight enough. It's not going to be a perfect straight line. That's fine. But this check the scatter plot, it's got to be approximately linear. Just like our histogram had to be unimodal and symmetric, in order to use the normal model. And the last one is the no outliers condition. And that's important because when you saw the formula for R, it's based off of z-scores. Outliers are going to have massive z-scores and therefore have massive influence on the value of R. So they can really make a misleading correlation coefficient if you have outliers present. So we cannot calculate correlation with outliers. All right, some properties of correlation is it always falls between -1 and 1. So it's a really nice kind of clean number in that way. And the sign, SIGN, the sign positive or negative corresponds to the direction of the association. So this single number gives us information about both the direction based on its sign and the strength based on its magnitude, which is phenomenal. And really the form as well, because you're only calculating this value if you have a linear relationship to start with. So values that are closer to +1 or -1 we'll consider strong. Values that are closer to 0 in either direction, we'll consider those weak. Values in the middle are going to be somewhat moderate. If it's exactly 1 or -1, that means it falls on a perfect straight line like you have in Algebra 1, which is really not going to happen very often for us. Another thing, it treats x and y symmetrically, so even if you switch the explanatory and response variables, that will not change the value R whatsoever. It has no units. We standardized everything by taking those z-scores. It's not affected by any kind of change in the units, any kind of rescaling. R will remain the exact same. So if you changed everything from meters to inches, your value of R would not change at all. And I cannot say this enough here. It measures the strength of the linear association between two variables. All right, there can be a very, very strong relationship in a scatter plot. Let's say the data is following almost a perfect quadratic. All right, this is a very strong association. But there's no correlation here. Okay, why? Because it's not linear. Okay, so if you were to calculate a value of R here, which you shouldn't do because it's not linear, you would get a very small value of R and think it's weak. Well, it's a strong association, but yes, it is a weak or no correlation because it's not linear. And as I said already on the previous slide, it is very sensitive to outliers just because of the way we calculate it with those z-scores. Just providing a nice visual kind of what different scatter plots look like with kind of their corresponding R values. And you notice starting up here at the top left, so a very strong positive, R is 0.9. And we kind of move down the scale, but kind of bouncing back and forth between positive and negative. So negative 0.8. You see here like positive 0.5. It's still linear, but getting a little weaker. There's a lot more scatter around the line in comparison to this one. And then down here, kind of in the bottom row, it's tough to even really figure out a linear relationship there at all. It's starting to kind of look more and more like a cloud of points as we approach R equaling 0. All the ones that are negative have the negative direction. All the ones that are positive have the positive direction. And just increasing scatter around the line, it's following that line less as the values of R get closer and closer to 0. How strong is strong? This is going to be kind of our guideline here. It's not a hard and fast rule, but things above 0.7 we usually say are strong, and that goes in either direction, so below negative 0.7. Things in the middle here between 0.4 and 0.7 we say are moderate. Things below 0.4 are said to be weak. So always just include the correlation coefficient with your description of the scatter plot. All right, so you can include it right there. They can judge for themselves what they think about it. A lot of it depends on the data as well. So how to find R? the first thing you need to do if you have not done this already is you need to go to the catalog on your calculator, which you'll do second and the number 0. And the catalog is just a list of all the things your calculator can do. It's quite a long list, and you're going to need to scroll all the way down to something called Diagnostic On, because for some reason the calculator does not have R kind of loaded in there to start with. So once you choose Diagnostic On, just hit Enter, and you should get it say like Done on the home screen. So once you've done that once, you will no longer need to do that again. So once you have that set up, this is a one-time thing. Great. And then where you're going to go to calculate R is you're going to head to the Stat Calc menu. And choose option 4, which is just linreg AX plus B. And you can also choose number 8, and it works the exact same. Let me just fix that. There we go. And what you want to enter there is you're just entering your data. So you just need to choose the right X list and Y list. If you have an older calculator, it's just going to pop up on the home screen. And you just want to enter your list separated by a comma. So you would just put L1, comma, L2. And then hit enter. And then it'll bring up a few different things. It'll bring up the regression equation, which we will talk about in the next chapter. It'll bring up something R squared, which we'll also talk about later. And the last value to bring up is R, and that value there is your correlation coefficient. Okay. You've probably heard this saying before, correlation does not mean causation. So what does that mean? Just because there's a strong association between two variables, or just because there's a strong correlation, a linear relationship between two variables, does not mean that the explanatory variable is causing the response variable. All right, there's endless examples online if you want to check this out. If you just Google correlation does not mean causation, you can get tons of examples. Here's one I just found. Down here, explanatory variable, fresh lemons imported to US from Mexico, and the corresponding response variable here is total US highway fatality rate. So what this is saying is as X is increasing here, as more lemons are imported from Mexico, all right, the traffic fatalities are decreasing. All right, and this is R squared up here. R squared is simply the correlation coefficient squared. And so notice that R value is very strong. All right, so there's a very strong relationship here, very strong correlation. Okay, but I think anyone with kind of common sense here could figure out the more lemons we import are not making any difference in the fatality rate, regardless what the scatter plot is showing. Here's another example. We have number of firefighters down here on the explanatory variable and the corresponding damage in dollars of the house. All right, so as more firefighters come to the fire, they're causing more damage. That is also not quite what's going on there. So what is going on here? If we can't say that one variable is causing the other, what's going on here is there a lurking variable. There's something else, another variable that is causing the kind of correlation between the two. In the firefighters versus damage, the lurking variable is the size of the fire. Why? Well, it's not like the firefighters are causing all the damage, but more firefighters are needed if there's a bigger fire, and therefore the bigger fires will cause more damage. We can never, ever say that one variable causes the other with simply a scatter plot and correlation coefficients. So words really matter. So never try and argue that one variable is causing the other. It's usually going to require kind of some form of judgment, and it's usually going to require an experiment. So for now, we are not ever claiming causation between our variables. Some possible lurking variables here. It's just a few more examples. Okay, we see there's a strong positive correlation between the foot length of K through 12 students and their reading scores. So as their foot size increases, apparently they get better at reading. What's actually going on there? Lurking variable of age. As they get older, their feet grow and they get better at reading. Students who use tutors, have lower test scores than those who don't. Wow, tutors aren't doing anything? No, it's kind of, I guess I'd say student ability is the lurking variable there. The students that are already struggling in the class are the ones that need the tutor. And the last one, a survey shows a positive correlation between countries with high cell phone use and life expectancy. So cell phone use causes people to live longer? No, the lurking variable there is probably wealth. And wealth of a country or wealth of a region or city, that is a very common lurking variable for a lot of different correlations between two variables. So watch out for that because you see that all the time, arguing different things like that in the media or online. Okay, this is just something called a correlation matrix or a correlation table. And all it is just showing the correlation coefficients between multiple variables. So basically, this is just like they have a few different sets. They've calculated people's weight, hours of sleep. I forget what this was from, some kind of exposure while sleeping, and their corresponding lifespan. And so each cell, obviously the correlation with itself is going to be 1 because it's the same variable. But so every single other corresponding correlation is here. So like the correlation between hours of sleep and weight in kilograms is this negative 0.307. So those two variables have a moderate or weak negative correlation. Over here, like hours of sleep and exposure while sleeping, those have a little bit more moderate negative correlation. Lifespan, exposure while sleeping, weak positive correlation. So all of those, it's just a way to display it when you have multiple variables. Okay. Just really kind of hammering home this point, I can't say this enough, the difference between correlation and association, because in English they are used interchangeably, in stats they are not. So correlation only refers to relationships between quantitative variables. Association is a much more general, vague term. It can talk about quantitative, it can talk about categorical variables, just describing general relationships. Correlation is only linear. Association, once again, a much more general term, can describe any kind of relationship, quadratic, logarithmic, exponential, anything you want. In correlation, we have this value, the R value, correlation coefficient. Association, we do not have any kind of numerical value for that. Makes no sense to report a correlation coefficient R if we're talking about categorical variables or we're talking about a quadratic relationship. Does not make sense. All right, one more thing to watch out for. Okay, so here we have a revenue versus temperature for a burger stand. So temperature outside, obviously in Celsius, and the revenue in dollars. Okay, we see there's a very strong association, okay, but it is just not linear. It's going to be a strong quadratic association. The thing to be careful here, all right, if you just simply kind of threw that data set in your calculator and calculated the correlation coefficient, you would have got 0.162, and great, you think it's going to be a weak positive linear association. All right, and you'd be totally wrong. Okay, so it's very, very important to check the scatter plot. Okay, scatter plot and correlation coefficient go hand in hand. You can't have one without the other. Okay, you would have been totally wrong describing that as a weak positive association, because it's not. It's a very strong association. It is just quadratic. Okay, a lot of times you can have a very high correlation coefficient with a nonlinear relationship as well. That's usually going to happen when you have some outliers. But just in general, always check the scatter plot. Don't try to make any determinations on what the data set looks like just from R. Pretty much will always lead you down the wrong path. One last thing here, just another revenue versus temperature for a burger stand. And looks like a nice strong linear correlation here, positive. Gotta make sure you watch out for that outlier. Okay, be very careful. What I said from the start is that these outliers have huge impacts on the value of R, and later on they'll have huge impacts on the values of our regression equations. So make sure you are looking out for them. Just like in the past, it could just be a data entry error. So that's something you should always watch out for. All right, and fix and delete it. One other thing is a lot of times in a scatter plot, a common error you'll get is something called dim mismatch. That means dimension mismatch, and that means definitely data entry error. It means your X list and your Y list have different numbers of values. So either you added an extra point or forgot one, and everything's all messed up. So that's what that means. Go back and check your lists and make sure you enter things correctly if you ever get that. So if you have outliers, you can calculate the correlation coefficient with or without to see really how much impact it has. If you can justify it and you're not really interested in including the model, you can leave it out. Make sure you can justify it. An example in this burger example is, let's say someone came by and paid $160 for 2 burgers, but that's not really going to happen very often. It's not really going to be useful to making predictions. But yeah, a single outlier can really dominate that correlation value just because of how they're calculated using z-scores. All right, that's all we got. The video is already quite long. I apologize for moving quickly, but wanted to get everything in a reasonable amount of time. Hope you enjoyed. See you later.